Okay, welcome to Let's Get to the Marks. Today I am going through a question, A-level chemistry question on proteins, amino acid sequencing, and chromatography. So let's get into it. Question three. Endomorphin 2 is a peptide with the amino acid sequence shown. TYR, PRO, PHE, PHE, NH2. Each amino acid is represented by a three-letter abbreviation. TYR is tyrosine, PRO is proline, PHE is phenylalanine. Figure 2 shows part of the structure of endomorphin 2, showing the TYR, PRO, PHE part of the molecule. So we now know that this bit here, where's my pen? There it is. All right, we know that this bit here shows us TYR, PRO, and PHE. That's what is shown by all of this section that we've got here in figure 2. Cool. Now, let me just zoom down so I can read the rest of the question. So 3.1, the NH2 at the end of the amino acid sequence of endomorphin 2 shows that the terminal functional group is an amide, not an acid. Complete the structure of endomorphin 2 in figure 2. So we just need to complete the end. So just in case you're wondering what the hell we got to do, they're saying they've shown us this. So that is what this is. They're saying, look, we've just shown you this, and they're asking us to complete it. So we need to add a PHE NH2 on the end, right? We need to add another phenylalanine and then a terminal group, which is NH2. We need to add that on the end. So we kind of got to look at this structure and work out what alanine is. And because PHE is the last part of this three amino acid structure, we can just find the final amino acid in the structure and then repeat it to make the next PHE. So if you find here, look, there's an amine group right there. Okay, that's an amine group. That must be the start of the final amino acid. And there's the carboxylic group. Remember, they have an amine at the start and an acid at the end, or you could have an acid at the start and an amine at the end, but this one starts with an amine, ends with an acid. This here is the R group, this whole section here. So let's redraw that. And all we need to do is put an N, an H, and we're just redrawing exactly what we've got going on here. We're just copying what they've already done. And excuse my D grade GCSE art skills. There's the benzene ring. What else have we got to do? I've got to come back down here, draw that. We need the carboxylic acid group. That's supposed to be an H. I don't know what that looks like. Right, we're almost done. Now, that is the PHE. We've just done a repeat of this amino acid here. So we've definitely done the PHE. We've now got TYR, PRO, PHE, PHE. We just need to do a terminal, which is NH2. Okay, and how did we know that? Well, they put it up there, PHE, NH2. That's the terminal group. And it also told us that the terminal functional group is an amide, not an acid. If it was an acid, this would be OH, but they told us it's an amide. Remember, an amide has the C-double-O bond and connected to a nitrogen atom with a hydrogen like an amine, and that becomes the amide group. This whole bit here is the amide group. So they told us that that's correct. Awesome. So you're going to get 1 mark, I guess, for the terminals. It's 2 marks and 1 mark for the PHE. Right, let's move on to the next question. It says, use the structure of figure 2 to draw the skeletal formula of proline. So again, we can do the same thing. We just got to work out what proline is. Now we know we've got TYR, PRO, PHE. So we already worked out what PHE is, so I can just circle that. That was the PHE. So we don't want to draw that. And now we need to just get rid of the TYR, which is the first structure. So TYR, we've got NH2. TYR is over here. This is its R group. Now, how do I know to get rid of this? There's an amine and there's a carboxylic acid. Remember, each amino acid begins or starts with an amine or ends with an amine and then has a carboxylic acid at the other end. So that there is going to be TYR. Okay, and that means if I circle it in blue, if you can just about make that out, that means that this here is the PRO. So what do we have there? We just need to draw the amino acid PRO. Now, bearing in mind, this is once it's had a peptide bond, um, that there is once they form that peptide link in the amino acids, they don't want us to draw that. They want us to draw the skeletal formula of proline. So when it's actually fully connected. So we need to add two H's there. And what do we need to add on the carboxylic group there? We need to add an OH, okay, because it's going to be returned back to its original structure. And do they want the skeletal structure? No, we don't have to do to draw the skeletal, we have to do skeletal. Okay, cool, cool, cool. Let's do that now. And just add the water molecule back in, right? So we're just going to copy that and add a water molecule back in. So there's my nitrogen. I'm going to add our hydrogen back in. Remember, we only want to add a water molecule back in because obviously it was removed in a condensation reaction. And so now I'm just smash on OH. And there we go. That is, maybe I need to draw the little bond in between there. And there we go. That's what we need to do. So look, I've added the OH back and I've added an H back here. And there we go. You might say to yourself, sir, but shouldn't we have two H's there? We can't really because it's part of this ring structure here. So um, nitrogen doesn't like four bonds. So it will then, I suppose you'll probably get the mark if you put an H there and a plus sign. But then you need to you only need to add one hydrogen. So we can probably actually, hold on one secondo. We can probably do this, which is basically doing the Zwitterion. So we can add the plus there, but then I'm going to need to get rid of that hydrogen and put a minus there. So that will get you the marks as well. But just bear in mind that you're still just adding two H's and an O, a water molecule back. So best bet for me is to whack that back and whack that there and go back to that. Okay, enough waffle. Let's zing to the next question. Okay, here we go. A student hydrolyzes a sample of endomorphin 2 to break it down into its constituent amino acids. The student analyzes the resulting mixture by thin layer chromatography, that's TLC, state a reagent and the conditions needed for the hydrolysis. So there's a number of ways you can break up a protein. If you're a biologist, you can say to use like some form of protease, the enzyme that will hydrolyze those peptide bonds. But as a chemist, we're just going to go with hydrochloric acid and we need to warm it or heat it. So warm it. Okay, so we're going to need to heat with hydrochloric acid. 3.4, figure 3 shows the apparatus used for the TLC. We've got a beaker, we've got a volatile organic solvent, we've got a TLC plate coated with silica, and we've got a mixture on the TLC plate. There is a piece of the apparatus missing from figure 3. The omission will result in an inaccurate chromatogram. Identify the missing piece of the apparatus, state and explain why this piece of the apparatus is needed. The kind of clue here that should trigger you into realizing what's missing. Well, there's two clues. Number one, you may spot immediately, should there be a lid on top? You'd be right. The thing that might trigger you into realizing there should be a lid on top is the volatile organic solvent. The word volatile means it's going to evaporate easily and the solvent is going to escape without a lid. If you keep a lid, then the atmosphere will be saturated with the organic solvent, even when it's evaporating, and it will prevent it from fully evaporating. Once the atmosphere is saturated, no more organic solvent will evaporate. So what we need to do is say the missing piece of equipment is a lid. Explanation, volatile organic solvent prevent evaporation and loss of volatile organic solvent. Why is that important? What's the issue with that? So we've just said what the problem is. Well, what's the effect? If we don't have a lid and the organic solvent escapes, what's the effect? Um, this will prevent the mixture moving up the plate. Or we could say it will cause the plate to dry out. So if the plate gets dry, then the mixture is no longer going to move up the plate, and we're not going to get a proper distance for the solvent front, or we're not going to be able to calculate the RF value accurately. Okay, so there we go. Let's put those marks in. One for the lid, one for the lid prevents the evaporation or loss of the volatile organic solvent. I mean, it doesn't really stop evaporation. The organic solvent is going to evaporate, but once it's saturated the atmosphere, you're going to reach an equilibrium where no more solvent evaporates, and that's what the lid will create. And then that will prevent the plate from drying out. 3.5, state why the amino acids separate on the TLC plate. So why is it that proline, tyrosine, and phenylalanine, why do they actually separate? And it's to do with the mobile phase and the stationary phase. So, for example, proline has a relative greater attraction to the stationary phase than it does attraction to the mobile phase than phenylalanine. Hence why proline has spent a greater amount of its time retained on the stationary phase than phenylalanine has. So the reason why amino acids separate is because they have different, so the amino acids have different relative attractions to the mobile phase and stationary phase. So they've got different attractions to the different amino acids have different attraction levels of attraction to the mobile phase and the stationary phase. There's a load of other ways we could word that. That would be good enough. We've mentioned stationary and mobile, and it's the fact that some of them prefer to spend more time retained on the stationary phase than they do attracted or dissolved in the mobile phase. You can talk about solubility as well. Different amino acids have different affinities. Instead of attraction, you can use the word affinity. Name a suitable developing agent. State why the developing agent is needed. Right. So at the end of this, once these different parts of the mixture, these different amino acids have separated out, we're going to want to calculate their RF value. And of course, in order to do that, we need to be able to see them. And one of the problems is amino acids are colorless. And so what we do is we cover the plate with a stain that will show the position of the different amino acids. And the stain we use is ninhydrin, a developing agent, I should say, not a stain. Amino acids are colorless. Ninhydrin will color them purple. So they end up looking purple once you add ninhydrin, and that means we can now go ahead and calculate the RF values. Awesome. And then the final part to this question, 3.7, determine the RF value for TYR. So all you need to do here to determine the RF value for TYR is get your ruler out and measure the distance. So this is your ruler. Measure the distance between the baseline and the solvent front. So first you're going to RF is equal to, you want this distance from the baseline to the solvent front, and that is the distance moved by the solvent. And then you're going to measure the distance between TYR, which is the particular amino acid we're interested in. You're going to measure the baseline to TYR. So you're going to divide the smaller distance by the bigger distance, and that will give you the RF value. And the equation to do that is distance moved by TYR. What a mixture of capitals. Right, yeah. Distance moved by TYR. And then you just want to divide that by the distance moved by the solvent front. Distance moved by solvent. And that gives you the RF value. And your RF value here is going to work out to be 0.54. And you can kind of see that it's just moved over half, just over halfway. You should never get an RF value greater than 1 because your mixture cannot have a greater affinity to the solvent than the solvent does to itself, essentially. And here we go. That's the final mark of that question. So make sure you leave a comment, hit the like. Let's get to the marks.